We can think of noise as the part of the target function that we can't model. This is a brief explanation, but we need to uncover more details. We can start by thinking of it having two sources. The first source is what we'll refer to as stochastic noise or data error. When we're trying to measure the target function, we might have errors in our sensor and actually end up observing a noisy target function instead. We usually assume that this stochastic noise is not dependent on anything in the dataset, and by taking different measurements of the same input, we would get different values because it's white noise. These are fluctuations in measurements in errors that we can't model at all. On the other hand, we also have deterministic noise. This is the case of model error or bias. These two mean the same thing. What we mean here is that we want to learn from the observations a particular average hypothesis, which would constitute how well our hypothesis set can learn the target function. When we underfit, just like in the sine function, we'll have a significant amount of deterministic noise. Deterministic noise just basically mentions the part of the target function we just can't model because our representation is too simplistic. Right? If we're trying to model an elephant and we're limited to a very simple representation like a cartoon graphic, we might get something out like on the right, but certainly it looks very different in fidelity compared to the image on the left. Both sources of noise hurt learning and contribute to the problem of not being able to minimize the test cost. We have stochastic noise that we see on the left-hand side that we started with. These are random measurement errors, and then oftentimes when we remeasure the target at that particular input, we would get a different value. Even if we change the hypothesis class, it wouldn't vary because it has nothing to do with the hypothesis class, just a problematic case when we are not very accurate at measuring the target at a particular input value. So changing H doesn't change anything about the stochastic noise. On the other hand, on the right-hand side, let's look at deterministic noise. This is when the learner's hypothesis function is simply too impoverished and cannot model what we've asked it to do. This is again the bias, and by remeasuring y it won't change, right? If we have different points that we're sampling on this blue curve with respect to different data sets that we take, the average over all of these is still going to be the same h star, which in this case looks like a second order polynomial. If we change the hypothesis set, however, our deterministic noise will go up or down depending on whether we're moving towards a more simple hypothesis class or a more complex one. If we move to a more simple class, the deterministic noise would go up and vice versa. The problem here is that we only get to observe, in most cases, a single data set. We don't get to choose which data set we get to draw from. And typically with a particular machine learner that's already been parameterized, in other words, your hyperparameters have been set, you have already dealt with a fixed hypothesis set. So there's no way to distinguish whether we're looking at stochastic noise or deterministic noise because we only get one shot. And our hypothesis class, when the learner is searching through it, is just going to fit whatever it sees and can't distinguish between what is actually the signal and what's actually the noise. Let's study this again through the noise and its relationship to bias variance. So you'll remember the decomposition that we had on bias variance. Bias was the deterministic noise, which is basically looking at how well the average hypothesis coming from the hypothesis set would be able to capture the actual target function. We can look at this as a midway point between f a particular HD and H bar, right? H bar represents the best particular hypothesis you could get after generating many specific data sets HD. And then F is a little bit farther along in fidelity. So here we're going in the direction of having better fidelity with the target function. We also had this first term here which looked at the variance. This was definitely dependent on the specific data set that we looked at and its expected value over all possible probable inputs x. Now we're going to ask ourselves, does this bias variance trade-off, does it also apply in the case where the target function is noisy? I think you should be able to answer that because you've seen it before in the pre-lecture. Here we're going to have a target function. It's going to have a epsilon noise term, and we're going to set the expectation of the epsilon noise term because we're just adding it ourselves. We're artificially inflicting, shall we say, some noise on the target function. We're going to say it's centered at 0 and has an expectation of 0 overall. So let's go ahead and derive what the bias and variance analysis looks like for the case where we have a noisy target function. So we'll start by just writing down the simple equation that we've written before, which is that given a sample data set, we are going to engineer a hypothesis consistent with the data, and we want to measure how badly it does against the actual target function represented by y. So we'll write this out as, again, against the expectation of the data set and the noise term epsilon now as an expansion, okay, of the hypothesis and the y value, right? So this is the y value that we're just expanding because now we have not just a target function but some noise. So we're going to subtract that term away. So if we move the subtraction in, this other term will also be a negative. We're going to do the next line again with respect to the epsilon and the data set. We'll have, make sure we have enough room for it. Again, the hypothesis on D. We're going to do the same trick we did before and add an H bar and subtract the H bar. And we have the same two terms that we're going to carry down as before. And what we'd like to do is do some association of these terms so that we can do the same type of analysis as before. So we're going to group the first two, the second two, and the last term by itself. So we'll have terms 1, 2, and 3 here. And we'll go ahead and write the next line. So expectation with respect to the data set and epsilon, and we're going to take, again, because we had to undo the square over here, right? We're going to take 2 copies of the first term, and we'll get that. H of D minus H. You're going to see that is going to end up as the bias plus the middle 2 terms. So we get to take 2 copies of the middle, take 2 copies of the first term. So this is our H bar minus f of x. So this is our variance, right? We need to find the hypothesis, the best possible hypothesis against the target function itself. I'm going to take 2 copies of the last term. This is our epsilon, our stochastic noise, squared. And we have a bunch of cross terms, right, which are going to take some mixture of all of these terms, right? Some ones of 2, 3, and 1, but all of the ones that have cross term with 3, because the expectation of epsilon being centered at 0 is equal to 0, all of the cross terms with 3 are going to go away. We're going to cross term with 1 and 2. We saw that actually the first term, this one here, the expectation of hd of x minus h bar of x, that's also going to be 0 because we defined, by definition, we defined h bar to be h of d in the limit where we took so many different h of d's, right? So the expectation of this is going to be the same as this. These two are going to be equivalent, and then we're going to get a 0. Okay, so all of our cross terms drop, and that means what we have here is actually the end game of it, right? So we have got 3 terms here. We're going to call this one stochastic noise. We're going to call our second term the bias or deterministic noise. And then we're going to call the first term the variance. So you have the derivation of this on the slide before that comes out nice and neat.